What if the greatest story ever told, the epic of our entire universe, has a missing first page? Not just a page, but the very first word, the opening sentence that sets everything else into motion. We have painstakingly pieced together the narrative tracing the cosmic chronicle back through 13.8 billion years of starlight and shadow of birth and death on unimaginable scales. We can read the tale of how galaxies coalesced like dew on a spider's web of dark matter, of how stars ignited from collapsing clouds of hydrogen, forging the elements of life in their thermonuclear hearts. We have decoded the faint ghostly afterglow of creation itself, a whisper from a time when the entire cosmos was a firestorm hotter and denser than the core of any sun. This story, our story, is a triumph of human curiosity. It is written in the language of mathematics and confirmed by the light of 1,000 billion galaxies. Following the thread of cosmic expansion backward, we travel on a journey that defies all terrestrial intuition. We watch as the grand, sprawling structures of the present-day universe dissolve. The familiar constellations, the Milky Way, the great Andromeda galaxy hurtling toward us, all of it merges back into a smooth, featureless, incandescent fog. This is a voyage not across space, but through time itself, rewinding the celestial clock with the full power of our scientific understanding. We see the very first stars, those colossal, short-lived titans of pure hydrogen and helium, disassembling themselves, their light racing backward into the darkness from which they came. Further back, we push into an era before a single star had ever shone, a period known as the Cosmic Dark Ages. For hundreds of millions of years, the universe was a vast, silent expanse of cooling gas, patiently waiting for gravity to gather the seeds of brilliance. Before that, for the first 380,000 years, the cosmos was utterly opaque, a searing, brilliant plasma of protons and electrons so hot and dense that light itself was trapped, bouncing endlessly between particles like a prisoner in a hall of mirrors. We can't see past this wall of light with telescopes, but we can see the wall itself. This is the cosmic microwave background radiation, the oldest light in the universe, a fossilized echo of our cosmic infancy, a baby picture of the cosmos, beautiful and profoundly informative. It tells us that the universe was once almost perfectly uniform, a smooth soup of primordial energy with ripples of truly minuscule size. Those tiny ripples, less than 1 part in 100,000, were the seeds of everything that would ever exist. They were the gravitational keystones around which all future structure, every star, every planet, every one of us would eventually form. This picture is the bedrock of modern cosmology, a triumphant confirmation of our Big Bang theory. From this simple, hot, dense beginning, we can simulate on our supercomputers the entire subsequent evolution of the universe, and what we get is a stunning match for the cosmos we observe around us today. Our theories work. They possess a terrifying, beautiful, predictive power. They allow us to read the history of existence from a single, static-filled snapshot of its youth. Armed with this confidence, we press on, emboldened to push our inquiry even further back into the inferno. We rewind past the moment that light was set free into the churning plasma itself. Here, conditions are so extreme that the familiar structures of matter cannot hold together. We watch as the first atomic nuclei forged in the first 3 minutes of time are torn apart by the sheer heat dissolving back into a sea of their constituent protons and neutrons. Further still, we plunge into the first second of existence. The pressure and temperature are now so titanic that protons and neutrons themselves cannot survive. They melt, their identities erased into their own fundamental components, a roiling, chaotic soup of quarks and gluons, the most basic building blocks of matter we know. Here, in this quark-gluon plasma, the universe existed in a state of pure raw potential. Our physics is still holding. The standard model of particle physics, our guidebook to the subatomic world, expertly describes the behavior of this exotic state of matter. We can even recreate it for fleeting microscopic moments in our most powerful particle accelerators. The story, though increasingly alien, remains coherent. The laws we have discovered on Earth still apply to the infant cosmos, and so we push back with ever more audacious resolve into the first microsecond, the first nanosecond. The energy of every single particle is greater than anything we can generate in a laboratory. The density defies all physical analogy. The entire observable universe, all of its matter and energy, all of that future starlight and potential for life, is compressed into a volume smaller than our solar system, then smaller than the Earth, then smaller than a pinhead. And then, as we rewind to the most extreme imaginable moment at a time of 10 to the minus 43 seconds after the very beginning we hit it, we come to an abrupt, violent, and absolute stop. Not against a physical barrier, but against a wall of pure, defiant nonsense. It is a boundary of our own ignorance, a point past which our science, our mathematics, and our very ability to describe reality utterly collapses. The cosmic story which we had been reading so fluently suddenly dissolves into an incomprehensible scrawl. The equations that have been our faithful guides through billions of years of cosmic history begin to scream, spitting out infinities and paradoxes. They break down. The physics we cherish, the rules that govern the universe with such elegant precision, simply cease to apply. This boundary, this impenetrable conceptual wall, is known as the Planck Epoch. It is the shortest sliver of time imaginable, a fleeting instant that holds the ultimate mystery. It is the horizon of our knowledge, a scientific event horizon beyond which we cannot see. To understand why this wall exists, why our journey back in time comes to such a catastrophic halt, you have to understand the two great pillars upon which all of modern physics rests. They are two of the most profound and successful creations of the human intellect, each a masterpiece of observation, insight, and mathematical beauty. Yet they are at their deepest cores fundamentally incompatible. They tell two different stories about the nature of reality. And in the crucible of the first instant, those two stories collide. The first pillar is Albert Einstein's general theory of relativity. This is the physics of the grand and the majestic. It is a theory of gravity, but not as a force in the conventional sense. In Einstein's universe, gravity is the geometry of spacetime itself. Massive objects like stars and galaxies don't pull on each other from a distance. They warp and curve the very fabric of reality around them. Planets orbit the Sun not because they are tethered by an invisible rope, but because they are following the straightest possible path through the curved spacetime created by the Sun's immense mass. Relativity is a theory of smooth, flowing, continuous elegance. It governs the graceful waltz of orbiting planets, the spiraling arms of galaxies, the majestic expansion of the entire universe, and the terrifying collapse of stars into black holes. Its predictions have been confirmed to an astonishing degree of precision. It predicted that starlight would bend as it passed the Sun, and it does. It predicted that time itself would run slower in a stronger gravitational field, a bizarre effect we now have to account for every single day to make our GPS systems function. It predicted the existence of gravitational waves, ripples in the fabric of spacetime, which we finally detected a century later, opening an entirely new window onto the cosmos. Relativity is our map to the large-scale universe. It is deterministic, classical, and paints a picture of a predictable cosmos where cause and effect rule with an iron fist. It is the language of the cosmos written on the largest possible canvas. The second pillar is quantum mechanics. If relativity is the physics of the majestic, quantum mechanics is the physics of the bizarre, the counterintuitive, and the incredibly small. This is the theory that governs the subatomic world, the realm of electrons, photons, and quarks. And the story it tells could not be more different from relativity's elegant cosmic ballet. In the quantum world, certainty dissolves into probability. Particles can be in multiple places at once until you measure them. They can tunnel through impenetrable barriers. They can become mysteriously linked or entangled across vast distances, so that measuring one instantaneously affects the other. The smooth, continuous fabric of reality, described by relativity, is replaced by a jittery, uncertain world of discrete packets or quanta of energy. Quantum mechanics is not a theory of elegant curves, but of statistical clouds of possibility. It is messy, strange, and deeply unsettling to our classical intuition. Yet, it is arguably the most successful scientific theory in human history. It is the foundation of almost all modern technology. The laser in your Blu-ray player, the transistors in your smartphone, the nuclear power that lights our cities, all of it is a direct result of our mastery over the quantum world. Our understanding of chemistry, of materials, science, of biology itself is fundamentally rooted in the probabilistic rules of quantum mechanics. It is our undisputed guide to the universe on the smallest possible scales. For nearly a century, these two great theories have lived in a state of peaceful, if slightly awkward, coexistence. Relativity has reigned supreme over the realm of the very large, and quantum mechanics has held absolute dominion over the realm of the very small. The universe is so vast, and atoms are so tiny, that for most practical purposes, their territories rarely overlap. A physicist studying the orbit of Jupiter doesn't need to worry about the quantum state of its individual atoms. A chemist studying a chemical reaction doesn't need to account for the minuscule gravitational curvature caused by a single molecule. The two theories could be used in their own domains, each brilliantly successful, their fundamental incompatibility a problem left for another day. But on our journey back to the beginning of time, that day arrives with cataclysmic force. As we approach the Planck Epoch, the entire observable universe is compressed into a space far, far smaller than a single atom. Suddenly, the territory of the very large and the territory of the very small are one and the same. The universe is simultaneously a single quantum particle and a gravitational object of unimaginable mass and density. It is here, in this singular infinitesimal point, that our two pillars of physics are forced into a direct confrontation. We need a theory of quantum gravity, a way to describe the quantum behavior of spacetime itself, and we do not have one. When we try to apply the equations of general relativity to a space that small, they tell us that spacetime should be smooth and gently curved. They predict a single point of infinite density, a singularity, but when we try to apply the laws of quantum mechanics, they give us a completely different and utterly violent answer. Quantum theory insists that on such tiny scales, nothing can be smooth or certain. The uncertainty principle, a core tenet of the quantum world, implies that spacetime itself should be a chaotic, roiling foam of energy. Tiny wormholes and short-lived virtual universes should be popping in and out of existence in a frenzy of quantum fluctuation. It should be a place where the distinction between space and time dissolves, where cause and effect lose all meaning. It is a vision of pure, untamed chaos. The two theories provide diametrically opposed descriptions of reality at this ultimate frontier. Relativity's elegant geometry and quantum mechanics' probabilistic chaos go to war. When we try to combine their equations to force them to work together in this extreme environment, the mathematics breaks down into a cascade of infinities. The probability of any given outcome becomes 100% a clear signal that the theory has reached its absolute limit and is producing gibberish. This is the wall. This is the Planck Epoch. A time before 10 to the minus 43 seconds, a temperature of 10 to the 32 degrees, a density beyond any form of description. It's not just that we don't know what happened, it's that our current physics is incapable of even asking the question in a sensible way. The moment the universe began is for now the moment our knowledge ends. It's the ultimate paradox. We stand at the threshold of existence itself, armed with the most powerful intellectual tools ever devised, only to find that they are rendered useless, shattered by the very object of our inquiry. The first page of the cosmic story isn't just missing, it appears to be written in a language we have not yet learned to read, governed by a set of physical laws we have not yet discovered. This isn't merely an academic puzzle, some esoteric detail in the grand cosmic story. The secret of what happened in that first unknowable instant, the physics of the Planck Epoch, likely holds the key to answering the deepest questions we can ask. Why is there something rather than nothing? Why does the universe have the specific properties it does? Are there other dimensions? Was our Big Bang the only one? The answers to these questions are almost certainly encoded in the physics that governed that first fraction of a second. They are locked away behind that mathematical wall, waiting for a new revolution in our understanding, a new theory that can finally unite the two warring pillars of our knowledge. So how do we possibly begin to explore a moment that is so remote in time and so extreme in nature that we can never hope to observe it directly? How do we pierce this veil of infinity? The quest to understand the beginning of everything starts not by looking further out into space, but by looking deeper into the very nature of reality itself. It begins not with a telescope, but with the power of a pure idea. There is a wall in time. It is not a place you can visit, nor a barrier you can touch, but it is the most absolute and impenetrable frontier we have ever discovered. It stands at the very beginning of existence, a shimmering curtain behind which the origin of our universe is hidden. For nearly a century, we have thrown the full force of human intellect against that wall, our most powerful theories, our most brilliant mathematics, our deepest insights into the nature of reality. And for nearly a century, we have watched them all shatter. Our destination in this journey is that wall. We seek the moment our physics breaks down, the instant before time itself had meaning. But to appreciate the sheer, terrifying magnitude of that breakdown, we must first appreciate the astonishing, miraculous success of the physics that takes us there. We must travel backwards from the familiar comfort of the present, deep into the primordial past, following the unbroken thread of cosmic history. This story, your story, begins not with a bang, but with the quiet hum of the cosmos we see today. You are living inside the grand, sprawling result of a 13.8 billion-year-old experiment. All around you, the evidence of its success is breathtakingly apparent. We inhabit a universe of intricate structure, a cosmic web woven from filaments of galaxies, each one a city of light containing hundreds of billions of stars. Look through our telescopes and you see this majestic architecture stretching for billions of light years in every direction. You see spiral galaxies like our own Milky Way pirouetting in a slow gravitational ballet. You see colossal elliptical galaxies, ancient behemoths formed from the chaotic mergers of their smaller kin. Between them lie vast dark voids, regions of profound emptiness that give the cosmic web its filigreed cellular shape. This is the universe in its stately middle age, a realm governed by laws we have come to understand with breathtaking precision. The force shaping this cosmic landscape is gravity, the gentle, persistent whisper that given enough time can command stars and assemble galaxies. We can model the dance of these galactic clusters on our supercomputers, simulating their formation with an accuracy that is nothing short of astonishing. We input the known ingredients: dark matter, the invisible scaffolding upon which galaxies are built; dark energy, the mysterious force accelerating the expansion of space; and the normal matter that makes up everything you can see and touch. We let the simulation run, and what emerges on our screens is a universe that looks uncannily like the one we observe. The patterns, the clusters, the voids, they all snap into place. Our understanding of gravity from Einstein's elegant equations of general relativity works. It describes the cosmic arena perfectly. And what of the players within that arena? The stars, the planets, you yourself. You are a collection of atoms forged in the heart of long-dead suns. How science can explain this too with a theory of equal power and elegance, the standard model of particle physics. It is our definitive field guide to the subatomic world. It tells us that everything you see is made of a surprisingly small number of fundamental building blocks, quarks which huddle together to form protons and neutrons and leptons, like the familiar electron. It also describes the forces that govern their interactions, the messengers that carry instructions between them. The electromagnetic force carried by photons binds electrons to atomic nuclei, making chemistry and life possible. The strong nuclear force carried by gluons glues quarks together with unimaginable strength, forming the very heart of matter. The weak nuclear force, more subtle, governs radioactive decay, the slow, transformative fire that helps power the stars. These two great pillars of modern physics, general relativity for the very large, the standard model for the very small, represent the summit of our quest to understand the cosmos. Together, they allow us to read the story of the universe forward from a much earlier, simpler time and see how it blossomed into the complexity we witness today. They explain how the first pristine clouds of hydrogen and helium, the universe's raw materials, collapsed under their own weight. We can calculate the immense pressures and temperatures that built up in their cores until they reached the ignition point for nuclear fusion. In that moment, the first stars were born, brilliant, massive, and short-lived cosmic blowtorches that lit up the primordial darkness. Inside these stellar furnaces, the simple elements of the early universe were cooked into heavier ones, The carbon in your DNA, the oxygen you breathe, the iron in your blood. When these giant stars died in spectacular supernova explosions, they seeded the cosmos with the ingredients for new stars, for planets, and eventually for us. Our theories don't just describe this process in broad strokes. They predict the precise elemental abundances we observe in ancient stars and distant galaxies. The physics works. It is tested, verified, and triumphant. But our journey is not forward into the future. It is a regression into the past, a pilgrimage to the source. So, let us begin to rewind the cosmic clock. We pull back from our magnificent, mature universe, and the galaxies rush towards us. The intricate web of structure dissolves as we travel deeper into the past. We fly backwards through eras of cosmic history, past the peak of star formation, past the birth of our own sun, to a time before any galaxies had formed at all. We are heading for a critical transition, a moment when the entire universe underwent a profound change of state. We push further and further back until we are some 38,000,000 years after the beginning. Here our journey hits what appears to be a wall of fire. In every direction we look, the universe is filled with a faint, pervasive, and almost perfectly uniform glow of microwave radiation. This is the cosmic microwave background, the oldest light in the universe, an echo of creation itself. For the first 38,000,000 years of its existence, the universe was an impossibly hot, dense, and opaque fog. It was a seething plasma of atomic nuclei and electrons, so energetic that light particles, photons, could not travel more than a few inches without being scattered. The cosmos was a prison for light. An observer then would have seen nothing but a blinding, featureless white glare in every direction. But as the universe expanded, it cooled. And at this precise moment, 38,000,000 years after the beginning, the temperature dropped to a critical threshold about the same as the surface of a cool star. For the first time, it was cool enough for electrons to be captured by the patiently waiting nuclei, forming the first stable neutral atoms of hydrogen and helium. Suddenly, with the free-roaming electrons now bound into orbits, the universe became transparent. The photons that had been trapped within the plasma were set free, and they have been traveling across the cosmos unimpeded ever since. What we detect today as the cosmic microwave background is the collective light from that exact moment of liberation, the universe's first baby picture. And what a picture it is! When our satellites like Planck and WMAP mapped this ancient light, they found it was astonishingly uniform. The temperature of the afterglow is the same to 1 part in 1,000,000 everywhere we look. This uniformity tells us that the early universe was in a state of near-perfect equilibrium, but it is in the imperfections, the tiny, almost imperceptible fluctuations in that temperature, where the true magic lies. These are not random noise. They are the fossilized imprints of quantum fluctuations from an even earlier time, stretched to astronomical proportions. They are the primordial seeds of all structure. The slightly hotter, denser spots in this ancient map represent the regions where gravity would have a slightly stronger grip. Over the next billion years, these minuscule seeds would grow, pulling in surrounding matter to become the first stars, the first galaxies, the first great clusters, the entire cosmic web. You are sitting in a structure that grew from a temperature ripple of a few millionths of a degree. Once again, our cosmological models, fed with the data from this ancient light, predict the evolution of these structures with uncanny accuracy. The physics works. It connects the largest structures we see today to the quantum shivers of the infant cosmos. Yet this is not the beginning. The formation of the first atoms was a monumental event, but it was merely one milestone on a much longer road. The light of the cosmic microwave background blocks our direct view of what came before, but our theories do not falter. They allow us to push through that wall of light and deduce what the universe must have been like in its even earlier infancy. To understand the hydrogen and helium atoms that formed at 38,000,000 years, we must ask where their nuclei came from. For that, we must rewind the clock again dramatically. We plunge backward in time past 1,000,000 years, past 1 year, past a single day. The universe is shrinking, becoming exponentially hotter and denser. With every moment we reclaim, we are heading for an era known as Big Bang nucleosynthesis, a period that lasted from just a few seconds to about 3 minutes after the beginning. Here in the first 3 minutes, the entire universe was a nuclear reactor. The temperature was measured in the billions of degrees, a searing heat far exceeding the core of our sun. The cosmos was a churning soup of protons, neutrons, electrons, and photons packed together with incredible density. In this primordial forge, the first atomic nuclei were hammered into existence. It was a race against time. The universe was expanding and cooling so rapidly that there was only a brief window of opportunity for nuclear reactions to occur. A free neutron, if left alone, will decay into a proton in about 15 minutes, but the universe was cooling much faster than that. As the temperature dropped, protons and neutrons could slam into each other, with enough force to overcome their mutual repulsion and stick together, bound by the strong nuclear force. A proton and a neutron formed a nucleus of deuterium or heavy hydrogen. Two deuterium nuclei could fuse to form a nucleus of helium-3, and those in turn could combine to create the incredibly stable nucleus of helium-4, made of 2 protons and 2 neutrons. The physics of this era is understood so precisely that we can calculate exactly what the outcome should be. The standard model of particle physics gives us the precise interaction strengths of the forces involved. General relativity tells us exactly how fast the universe was expanding and cooling. We can put these numbers into our equations and predict the primordial elemental cocktail that should emerge from this 3-minute furnace. The theory predicts that the universe should be composed of roughly 75% hydrogen nuclei, about 25% helium-4 nuclei, and tiny trace amounts of deuterium, helium-3, and lithium. And when we point our telescopes at the most ancient pristine gas clouds in the distant universe, clouds that have been largely untouched since this era, we find exactly those abundances. It is one of the most stunning and powerful validations of the entire Big Bang model. The fact that we can accurately predict the chemical composition of the infant universe from a time when it was only minutes old is a profound testament to the power of our science. The physics holds. It is as solid here in the crucible of the first 3 minutes as it is in the heart of a modern star. But our journey must continue. 3 minutes may seem close to the beginning, but in the logarithmic timescale of the early universe, it is an eternity. We must go deeper. We rewind past the first minute, past the first second. At 1 second old, the universe was too hot, even for protons and neutrons to form stable nuclei. Now, we plunge further still into the first microsecond of existence. At this stage, the temperature has soared into the trillions of degrees. The density is so extreme that it beggars all comparison, like compressing the mass of a mountain into the size of a single atom. Under these conditions, matter, as we know it, cannot exist. Protons and neutrons themselves dissolve. We have reached the era of the quark-gluon plasma. Here, in this unimaginably energetic state, the universe was a seething primordial soup of its most fundamental constituents. Quarks, the building blocks of protons and neutrons, roamed freely unbound by the strong force. They were accompanied by their antimatter counterparts, and by the gluons, the very carriers of that strong force which zipped between them. This was a liquid-like state of matter, a perfect fluid of pure potentiality, where the familiar particles of our world had not yet condensed into being. It was a time of perfect symmetry, a roiling chaos from which the order of our universe would eventually emerge. We have even managed to recreate fleeting microscopic droplets of this primordial state in our most powerful particle accelerators, like the Large Hadron Collider. By smashing heavy ions together at nearly the speed of light, we can, for a fraction of a second, reproduce the conditions of the first microsecond. The properties of the plasma we create in these experiments match the predictions of our theories perfectly. We have reached back into the first millionth of a second of time and confirmed that our physics, our standard model, still holds true. It is a staggering achievement. The thread of our understanding remains unbroken. But the beginning is closer now, and the conditions are growing more extreme with every step we take backward. To go further, we must confront a moment of truly cosmic violence, a period that reshaped the universe and set the stage for everything that followed. We wind the clock back from 1 microsecond to a mere trillionth of a trillionth of a trillionth of a second after the beginning. We have arrived at the epoch of cosmic inflation. This is not a period of gentle expansion, but of hyper-acceleration, a moment when the fabric of space itself expanded faster than the speed of light. In a sliver of time so small it is almost meaningless to us, the universe swelled from a size smaller than a proton to something larger than a grapefruit. This mind-boggling event, though lasting for only an infinitesimal moment, solves some of the biggest puzzles of cosmology. It explains why the universe appears so geometrically flat, and why the cosmic microwave background is so astonishingly uniform across vast distances that should never have been in causal contact. Inflation took the microscopic quantum jitters of spacetime and stretched them to astrophysical scales. Those quantum fluctuations became the macroscopic seeds of structure we later see imprinted on the cosmic microwave background. This theory, as wild as it sounds, is our best explanation for the large-scale properties of the cosmos. The detailed patterns of those tiny temperature variations in the CMB are a stunning match for the predictions made by inflationary models. It seems that even here, in this moment of unimaginable exponential growth, our theories continue to guide us. We have followed a chain of evidence and logic backwards from the galaxies of today to the afterglow of creation, from the forging of the first nuclei to the primordial soup of quarks, and now to the explosive instant of inflation that set the very scale of our cosmos. Each step of the way, our physics has been a reliable torch in the darkness, illuminating the path. We seem to be on the verge of the final answer, the ultimate point of origin. The thread has led us this far. But this is where the path ends. We stand at the precipice. The triumphs of the Standard Model and general relativity, the very tools that have brought us on this incredible journey, are about to become our undoing. Because as we try to take that final step backward through the inflationary epoch to time zero itself, the thread snaps, the torch sputters and dies. We have arrived at the edge of the map, at the boundary of known physics. We have reached the wall. Our journey back has become a descent into a crucible. We have crossed the threshold where the familiar forces of our universe, once distinct and sovereign, had merged into a single, unified power. But now, as our temporal rewind accelerates, hurtling us ever closer, the pressure inside this cosmic egg is building to an impossible crescendo. The entire observable universe, all its future galaxies and stars, every planet and every potential for life, is compressed into a volume so infinitesimally small it defies any earthly frame of reference. Here, a billionth of a trillionth of a trillionth of a second from the beginning, the temperature is not measured in millions or even billions of degrees. It is a furnace of 10,000 trillion degrees. An energy so concentrated that the very concepts of matter and force particle and field begin to lose their meaning, blurring into a primordial seething plasma of pure unbridled potential. We are approaching a wall, not a wall of fire or energy, but a wall of understanding. For it is here in this unimaginable furnace that the two great pillars of modern physics, the twin theories upon which our entire comprehension of the cosmos is built, are set on a collision course. For a century they have reigned supreme in their own domains, two monarchs ruling over separate vast empires of reality. On one side you have the majestic sweeping law of general relativity. This is Albert Einstein's masterpiece, a symphony of geometry and gravity. It is a theory of the immense, the cosmic, the grand ballet of celestial bodies. Relativity paints a picture of a universe that is elegant, predictable, and smooth. It gives us a stage for this cosmic drama, a four-dimensional fabric called spacetime. This fabric is not merely a passive backdrop, it is a dynamic entity. Matter and energy tell spacetime how to curve, and in return, the curvature of spacetime tells matter and energy how to move. It is a grand cosmic conversation. A star, a planet, a galaxy, they are not pulled by some mysterious invisible rope. They are simply following the straightest possible path through a universe that has been warped and contoured by the presence of mass. Gravity in this beautiful vision is not a force at all. It is the shape of space, the flow of time. Imagine a river. For relativity, space-time is like the deep, powerful current. Objects within it are like rafts and ships carried along by its flow. A massive star is like a deep whirlpool bending the currents around it, inexorably drawing in anything that ventures too close. A speeding planet is just a vessel navigating these cosmic currents. The equations are precise, deterministic. If you know the positions and masses of the objects, you can predict their dance for eons to come. It gave us the physics of black holes, the bending of starlight, the subtle wobble in Mercury's orbit, and the gravitational waves that now ripple across the cosmos, carrying the echoes of distant cataclysms. It is a theory of profound certainty, a clockwork universe on the grandest scale. The universe, according to Einstein, does not play dice. Then we turn to the other monarch, quantum mechanics. If relativity is a sweeping symphony, quantum mechanics is a chaotic jazz improvisation. It is the law of the microscopic, the realm of the particle, the atom, the photon, and its reality is utterly fundamentally different. It is a world built not on certainty but on probability, not on smooth curves but on discrete quantized packets of energy. Here, particles are not solid little marbles with definite locations. They are ghostly clouds of possibility described by a wave function. A particle can be in multiple places at once in a state of shimmering superposition until the moment we measure it, forcing it to commit to a single reality. This is a universe where things can tunnel through impossible barriers, where particles can become mysteriously linked or entangled across vast distances, their fates intertwined in an instant. It is a world governed by the uncertainty principle, a core tenet which states that there is a fundamental limit to what we can know. The more precisely you measure a particle's position, the less precisely you can know its momentum, and vice versa. It's not a limit of our instruments. It is an intrinsic property of reality itself. The universe at its smallest scale is fundamentally fuzzy, jittery, and uncertain. It absolutely unequivocally times play dice. For all of modern history, these two theories have coexisted peacefully. Relativity governs the planets, the stars, the galaxies, the cosmic expanse. Its domain is the very large, where gravity is the undisputed king, and the strange fuzziness of the quantum world averages out into irrelevance. Quantum mechanics governs the atoms, the electrons, the forces that bind matter. Its domain is the very small, where gravity is so astonishingly weak compared to the other forces that it can be almost completely ignored. They are like two perfect maps of the same globe, one showing the vast political empires, the other detailing the intricate local topography of individual cities. Both are correct, both are essential, as long as you don't try to use them on the same scale. But here, in the first sliver of a second of existence, that peace is shattered. The truce is broken. We are no longer in a realm of the very large or the very small. We are in a realm that is both simultaneously. The entire universe is smaller than a single proton, a scale where quantum mechanics must reign supreme. Yet the density of energy is so immense, so astronomically high, that the gravitational forces it generates are titanic, unimaginable. A force so strong it rivals the other fundamental forces of nature. This is the domain of general relativity. For the first and only time in cosmic history, the empires overlap. The two monarchs are forced into the same room, a room smaller than an atom, and they are asked to agree on the laws of reality. And the result is a catastrophic failure, a breakdown of physics itself. Here's where the conflict becomes unavoidable. General relativity, remember, requires a smooth, continuous, well-behaved spacetime. It needs a stable stage, a predictable canvas upon which to paint its elegant geometry. The curvature might change from place to place, but at any given point, spacetime itself is definite. It has a single, unambiguous shape. But quantum mechanics, with its inherent uncertainty principle, rebels against this. It tells us that on incredibly tiny scales, nothing is ever truly at rest. There is a constant, unavoidable jitter, a sea of quantum fluctuations. Pairs of virtual particles, matter and antimatter, are constantly blinking into and out of existence from the energy of the vacuum itself. The vacuum of space is not empty. It is a roiling, seething foam of activity. Now, let's bring gravity back into this quantum picture. Einstein taught us that energy and mass are two sides of the same coin, with his E equals mc squared. He also taught us that energy and mass are what warp space-time. When those quantum fluctuations cause virtual particles to pop into existence for a fleeting moment, they possess energy. And that energy, however, briefly must generate its own gravity. It must create its own tiny microscopic warp in the fabric of spacetime. On the scales of our everyday universe, this effect is so small it's completely negligible. The gravitational pull of a few virtual particles is lost in the cosmic noise. But in the primordial furnace, this is no longer true. The energies involved are colossal. The scales are microscopic. The uncertainty principle now applies not just to particles, but to spacetime itself. If you try to zoom in and look at a very, very small region of space, you are trying to pinpoint a location with extreme precision. Quantum uncertainty dictates that to do this, you must contend with a correspondingly huge uncertainty in energy and momentum within that region. The energy fluctuations become wild and violent. And these violent energy fluctuations create, according to relativity, equally violent and chaotic curvatures in the fabric of spacetime. The result is a reality that defies all logic. The smooth, elegant canvas of Einstein's universe is torn to shreds. At this ultra-microscopic level, spacetime is no longer a gentle river. It becomes a chaotic, boiling ocean of uncertainty, a turbulent quantum foam. Space and time are no longer continuous. They are a churning frenzy where tiny transient black holes might be constantly forming and evaporating. Wormholes, fleeting tunnels to who knows where could be bubbling into existence only to vanish in the next instant. The very geometry of reality becomes a probabilistic storm. This is the heart of the contradiction. To calculate the quantum state of the universe, you need a stable background of spacetime in which to perform your calculations. But to calculate the shape of spacetime using general relativity, you need to know how matter and energy are distributed. But that distribution is governed by quantum uncertainty, creating a spacetime that is anything but stable. Each theory requires the other to be stable and predictable, yet each theory renders the other chaotic and unknowable. It's a circular argument with no solution. It's a snake eating its own tail. The mathematics simply breaks down. When you force the equations of relativity and quantum mechanics together at this scale, they don't give you a fuzzy or an approximate answer. They give you infinities. They give you nonsense. They scream at you that the very questions you are asking about a specific location or a specific moment in time are meaningless. Imagine trying to map the surface of the ocean during a hurricane. You can't. The very concept of a stable surface no longer exists. There are only chaotic, unpredictable peaks and troughs constantly in motion. This is what happens to space-time. Our concepts of here and there, of before and after, begin to dissolve. Causality, the fundamental principle that an effect must follow its cause, becomes suspect. If time itself is fluctuating, twisting back on itself in microscopic loops, how can you definitively say that one event caused another? The linear progression of time, the arrow that has guided us all the way back, shatters into a million, shimmering, uncertain possibilities. This is not just a failure of our equations. It is a profound statement about the nature of reality. It suggests that space and time, which we perceive as the most fundamental aspects of our existence, the very stage on which everything happens, are not fundamental at all. They are emergent properties, like the wetness of water which emerges from the interactions of countless individual H2O molecules, but is not a property of any single molecule. Perhaps space-time itself emerges from a deeper, more primordial level of reality that is utterly alien to us. A reality where there is no space and no time, only pure information or mathematical relationships, or something our minds have not yet evolved to conceive. We are standing at the edge of a precipice, looking down into an abyss where our most trusted guides have abandoned us. The two most successful theories in the history of science, theories that can predict the behavior of the universe with breathtaking accuracy from the scale of a quark to the scale of a quasar, have declared themselves invalid. They have told us in the unforgiving language of mathematics that they cannot take us any further. The map we have been using to navigate our journey into the past has just gone blank. To proceed from here to take the final infinitesimal step towards the absolute beginning, we cannot rely on the physics we know. We are in uncharted territory, and we need a new kind of map. We need a new language, a new law that can unite the warring kingdoms of the quantum and the cosmic. A single framework that can speak of gravity in the language of probability and describe a universe where the stage itself is part of the quantum play. This is the holy grail of modern physics, the search for a theory of everything. And to understand what that theory might look like, we must now venture beyond the known into the speculative and a world of truly breathtaking ideas. A world of vibrating strings, extra dimensions, and quantized space itself. Our journey back to the origin of everything has brought us through eons of cosmic history, past the birth of galaxies, beyond the formation of the first atoms, and into the searing plasma of the universe's first seconds. We have witnessed forces splitting apart one by one like a divine shattering of some primordial symmetry. Yet even in that maelstrom in the grand unified epoch we just departed, a semblance of knowable physics remained. There were rules, however exotic. There was a space to expand and a time to flow forward. But now we must take the final step, a leap across an abyss so profound that it represents not just another chapter in the cosmic story, but the point where the book of physics as we know it is slammed shut, its language turning to utter nonsense. We are pushing our theoretical vessel into the final infinitesimal sliver of a second before this boundary into the last bastion of comprehensible reality. The pressure builds, the energy concentrates, and the very fabric of existence begins to groan under a strain it was never meant to endure in a classical sense. We are approaching the wall, not a wall of fire or matter, but a wall of pure ignorance, a shimmering curtain of impossibility that has taunted scientists for a century. This is the threshold of the Planck Epoch. To even speak of it, we must recalibrate our minds, for our intuitive sense of time and space is about to be violently dismantled. The boundary we are crossing is not arbitrary. It is etched into the deepest mathematical structure of reality. It is called the Planck time, a unit so terrifyingly brief it makes a nanosecond look like an eternity. 1 Planck time is 10 to the minus 43 seconds. Let that number sink in. There are more units of Planck time in a single second than there are atoms in all the known galaxies of the universe, multiplied 1 billion times over. It is the absolute smallest tick of the cosmic clock that our current physics can countenance the quantum of time itself. Before this moment, the very concept of before ceases to have any meaning we can grasp. And as we cross this temporal event horizon, the universe around us has shrunk to a scale that is equally absurd, a domain smaller than the Planck length, that's 10 to the minus 35 meters. Imagine an atom. Now zoom in on its nucleus. Now imagine a single proton within that nucleus. The leap in scale from that lone proton down to the Planck length is vastly greater than the leap from that same proton all the way out to the orbit of Neptune. You, I, our planet, our entire galaxy, everything we have ever known or conceived of was compressed into a volume so infinitesimally small that it defies all physical description, a point of near infinite density. And the temperature in this nascent cosmos, it is a furnace so far beyond our experience that it renders all analogies useless. Not the core of a star, not a supernova, not even the collision of 2 neutron stars could begin to approach this ferocity. We are in a realm where the temperature has soared past 10 to the 32 Kelvin, the Planck temperature. At this energy, the kinetic violence is so extreme that particles are not merely jostled, they are obliterated. The distinction between matter and energy becomes a moot point. The very fields from which particles arise are boiling with a vigor that would tear apart the structure of protons, neutrons, and quarks, reducing them to their most fundamental energetic state. This is not a fire. It is the source code of reality, running at a speed and temperature so high that the ordinary laws of thermodynamics are subsumed into a new, more profound and terrifying order. Here, in this crucible of creation, the universe is not just hot and dense. It is something else entirely. It is a state of pure, violent, and magnificent unity. A unity our science has dreamed of but never directly witnessed. In this unimaginable state, the 4 fundamental forces of nature which have dictated the evolution of the cosmos for 13.8 billion years are no longer separate entities. Gravity, the grand architect of cosmic structures, which we see as a gentle long-range curvature of spacetime. Electromagnetism, the force that binds atoms and paints the universe with light. the strong nuclear force, the unyielding glue that holds atomic nuclei together. And the weak nuclear force, the subtle agent of radioactive decay and stellar fusion, here in the Planck Epoch they are all gone, not destroyed but unified. They have merged their individual identities, dissolving into a single, majestic, all-powerful superforce. Imagine a perfect, flawless crystal. When you shine a light through it, the light splits into a rainbow of distinct colors. For billions of years, we have lived within that rainbow, studying each color, each force as a separate phenomenon. But here at the beginning, we have returned to the crystal itself. We are seeing the pure white, unsplit light of a single, unified interaction governing all of existence. Every event, every particle, every flicker of energy is a manifestation of this one solitary law. It's a symphony played by a single, infinitely complex instrument, a unified field theory made manifest in the heart of the Big Bang. This is the holy grail of physics, the ultimate simplicity from which all the complexity of our universe would later crystallize and fall. Yet this beautiful unified state conceals a paradox of monstrous proportions, a serpent coiled at the heart of creation. The problem lies with gravity. Throughout cosmic history, gravity has been the odd one out. The other three forces are described with stunning precision by the language of quantum mechanics, a world of probabilities, uncertainties, and discrete packets of energy. But gravity has always resisted. It is the domain of Albert Einstein's general relativity, a classical theory of smooth-flowing continuous spacetime. These two theories, quantum mechanics and general relativity, are the twin pillars of modern physics. They work perfectly in their own realms, the quantum world of the very small and the relativistic world of the very large. But here in the Planck Epoch, their realms collide with cataclysmic force. The extreme density means that the curvature of spacetime, which is how relativity describes gravity, is incredibly sharp and violent. At the same time, the minuscule scale means that quantum effects, the uncertainty and fuzziness of reality, are not just present, they are dominant. Every particle, every blip of energy carries with it a gravitational field, and in this dense quantum soup, those fields are fluctuating wildly, unpredictably from one instant to the next. This is where reality as we know it begins to fray at the seams. On this scale, Einstein's elegant geometric vision of spacetime as a smooth, rubber-like sheet breaks down. The quantum uncertainty principle takes hold of gravity itself. The curvature of space is no longer well defined. At one point, it might curve this way. An instant later, it might curve another. The fabric of spacetime is no longer a fabric at all. It is torn apart into a chaotic, bubbling, probabilistic mess. Physicists have a haunting name for this theoretical state, the quantum foam. Try to imagine it. Try to conceptualize a place where the very notions of here and there become meaningless. You cannot point to a specific location because location itself is a quantum blur, a haze of possibilities. Distance, the measure between 2 points, fluctuates so wildly that it is no longer a fixed quantity. A short distance can randomly become a long one and back again in an impossibly small fraction of a second. Wormholes, tiny fleeting tunnels through space-time, might be spontaneously erupting and vanishing all around you, connecting every point to every other point in a maddening, chaotic web. The smooth landscape of reality has been replaced by a violent, unpredictable tempest on the Planck scale, and with the breakdown of space comes the breakdown of time. Time, according to Einstein, is inextricably linked to space. One cannot exist without the other. In this quantum foam, where space is a churning sea of probability, the steady forward march of time dissolves. What does before and after mean when the timeline itself is bubbling and fluctuating? Cause and effect, the most fundamental principle of our logical universe, loses its foundation. An effect might precede its cause. A moment in time might loop back on itself. The linear narrative of the universe, from past to present to future, shatters into a disconnected set of possibilities, a now that has no clear connection to what came before or what will come next. You are adrift in an ocean where there is no up or down, no left or right, no forward or backward. You are in a place where the very grammar of existence has been erased. This is not just a failure of our imagination, it is a failure of the fundamental logic that underpins all of science. We have reached a point where the universe is so alien, that it is actively hostile to the concept of order itself. This is the ultimate anarchy, a realm where space-time is not a stage for events to play out upon, but is itself a violent probabilistic participant in its own chaotic creation. This brings us to the core of the crisis, the moment our mathematics, our proudest and most powerful tool for describing the cosmos, finally throws up its hands and admits defeat. When we try to apply the equations of general relativity and quantum mechanics to the conditions of the Planck Epoch, they don't just give us strange or counterintuitive answers. They give us no answers at all. The equations break. They literally scream out a single, nonsensical result: infinity. In physics, an infinity is not a number. It is a warning sign. It is a catastrophic failure of the theory, a declaration that the model of reality you are using has been pushed beyond its limits and is no longer valid. The calculated values for energy density, for spacetime curvature, for the strength of the quantum fluctuations, they all spiral out of control to infinity. It's like asking a calculator to divide by zero. The machine freezes, unable to compute an answer that makes any logical sense within its own system. Our physics is that calculator, and the Planck Epoch is the ultimate division by zero. It is the universe telling us in the starkest mathematical language possible: you cannot use these rules here. Your laws are invalid. Your science is broken. This is a moment of profound humility for science. The two great intellectual triumphs of the 20th century, the very theories that allowed us to predict the existence of black holes, to build GPS systems, to create the digital world, the theories that explain everything from the shimmer of a soap bubble to the thermonuclear furnace of a distant star, are shown to be nothing more than approximations. They are brilliant, incredibly successful descriptions of a low-energy, placid universe, our universe, but they are not the final word. They are like a detailed map of the coastline of a continent, completely useless for navigating the deep, stormy and unknown ocean beyond. The infinities that plague our equations are not a property of the early universe itself. They are ghosts in our machine, the mathematical signature of our own deep ignorance. They represent the precise boundary where our known physics ends, and where a new, deeper and more fundamental theory must take over. A theory we do not yet possess. A theory that can somehow weld the probabilistic, chaotic world of the quantum with the smooth, geometric world of gravity into a single, coherent whole. A theory of everything. And so we find ourselves suspended at this ultimate frontier. We are at 10 to the minus 43 seconds, staring into the abyss of a universe whose operating system we can no longer read. Behind us lies the entire sprawling epic of cosmic evolution, a story we have pieced together with remarkable success. But ahead of us lies only a question mark of infinite density. Space-time has dissolved into a foam of pure chaos. The fundamental forces have merged into an unknown unified state, and our equations have collapsed into meaningless infinities. We are standing on the edge of the known world, looking at the birthplace of reality itself, and we find that it is shrouded in a fog of our own making, a fog generated by the limitations of our own understanding. To pierce this veil, to understand what happened in the very first moment of creation, and what, if anything, came before it, we must abandon the physics that has served us so well. We must seek out a new language, a new mathematics, a new vision of reality itself. We must venture into the speculative, mind-bending world of theoretical physics, where ideas like vibrating strings and loops of space-time quantum challenge the very foundations of everything we thought we knew. The Planck Epoch is not an end. It is a violent, beautiful, and terrifying beginning, and a direct invitation to build a new kind of science. And so we find ourselves stranded at the edge of existence, staring into a blinding fog from which our universe was born. Behind us lie the twin pillars of 20th century physics, the magnificent edifices of general relativity and quantum mechanics. For a century they have guided us, allowing us to chart the cosmic oceans and map the atomic continents. But here at the shoreline of the Planck Epoch, their languages become mutually unintelligible. Their laws devolve into contradictions. The smooth, flowing geometry of Einstein's universe shatters against the violent, quantized frenzy of the subatomic world. This is not merely a gap in our knowledge, It is a fundamental schism in our understanding of reality itself, a place where our maps don't just end, they actively contradict one another, screaming that something is profoundly wrong with our most cherished ideas. We cannot simply build a bridge across this chasm. We must invent an entirely new form of physics, a theoretical language that can speak of both the gravitational titan and the quantum ghost in a single, coherent sentence. This desperate, exhilarating, and perhaps impossible quest is the search for a theory of quantum gravity. It is the holy grail of modern physics, a theory that would not just unite our conflicting views of the universe, but would provide the grammar for creation itself, allowing us to finally read the first word in the cosmic story. For decades, humanity's most brilliant minds have ventured into this intellectual wilderness, armed only with mathematics and imagination. Out of that wilderness, two rival paths have emerged, two radically different visions of the ultimate nature of things. They are less like competing theories and more like incommensurable philosophies, each demanding we abandon our deepest intuitions about the world. One path asks us to believe that the universe is a symphony, a grand orchestra of unimaginably small vibrating strings. The other asks us to see the universe as a mosaic, assembled from indivisible granular tiles of spacetime itself. Both claim to hold the key to the Planck Epoch. Both, if true, would mean that the world you think you know is but a faint shadow of a much stranger and far more beautiful reality. The first of these grand attempts to heal the schism in physics begins not with gravity but with the particles. It looks at the bewildering zoo of fundamental particles we've discovered, the quarks, the leptons, the bosons, and it asks a deceptively simple question: what if this complexity is an illusion? What if, beneath it all, there is only one fundamental ingredient? This is the revolutionary premise of string theory. It proposes that if you could zoom in on an electron closer than any microscope could ever take you past the quantum foam, down to the fundamental bedrock of existence, you would not find an infinitesimal point. You would find something with length, a tiny one-dimensional filament of pure vibrating energy, a string, and in that single elegant leap of imagination the universe transforms. It is no longer a collection of disparate billiard balls, but a single coherent musical instrument. Every particle, according to this idea, is just a different note played on the same fundamental string. An electron is a string vibrating in one particular pattern. A photon, the particle of light, is the same kind of string, just vibrating in a different pattern, a different note. The up quark, the gluon, the neutrino, all of them are simply different resonant frequencies, different harmonics in a grand cosmic symphony. You, the world around you, the distant stars are all composed of this single underlying substance, playing an infinitely complex chord that we call reality. It's an idea of breathtaking elegance, reducing the cacophony of the particle zoo to the sublime simplicity of a single violin. But to achieve this beautiful unification, string theory makes an extraordinary demand. It requires a new stage for its music to be played upon. The vibrations that produce the particles we know and love are not possible in our familiar three dimensions of space and one of time. The mathematics, the very self-consistency of the theory, insists that the universe must possess additional hidden spatial dimensions. These are not dimensions like length, width, and height, which stretch out to infinity. Instead, they are microscopic, curled up on themselves at every single point in our space, smaller than the nucleus of an atom, forming intricate, invisible geometric shapes. Imagine a garden hose. From a great distance, it looks like a simple one-dimensional line, but for a tiny ant walking upon its surface, it has a second dimension, the circular path around the hose's circumference. String theory proposes that our universe is like that hose. At every point in the space you inhabit, there exists a tiny, complex, multi-dimensional space, a shape known as a Calabi-Yau manifold, too small for us to ever perceive directly, yet its geometry is everything. The precise shape of these hidden dimensions dictates the way the strings can vibrate. It acts as the tuning peg for the universe, determining which notes are possible and which are forbidden. The constants of nature, the strength of electromagnetism, the mass of the electron are not arbitrary numbers. In string theory, they are encoded in the geometry of these extra dimensions. If we could map that invisible shape, we could in principle derive all the laws of physics from first principles, and within this symphonic framework, gravity finds its natural place. For decades, the graviton, the hypothetical quantum particle of gravity, had been a theoretical nightmare, a mathematical ghost that refused to be incorporated into the standard model of particle physics. But in string theory, it appears without being asked. It emerges effortlessly from the mathematics. One particular vibration mode of a tiny closed loop of string has the exact properties required of the graviton, a massless particle with spin 2. It is not an addition or an afterthought. It is an inevitable consequence of the theory. Gravity, the force that shapes galaxies and bends space-time, is revealed to be just another note played on a fundamental string. This was the moment string theory first announced itself as a true contender for a theory of everything. It didn't just unite the particles, it seamlessly wove Einstein's theory of gravity into the quantum tapestry. It provided a picture of what happens when two graviton strings interact, a calculation that produced nonsensical infinities in all previous theories, but yielded a finite, sensible answer in the language of strings. It seems to tame the violent chaos of the Planck Epoch, smoothing out the infinities by replacing point-like interactions with the gentler collisions of extended strings. It offers a vision of the singularity not as an endpoint of physics, but as a dense, hot state of stringy matter governed by laws that are complex but not impossible. It promises a universe born from the beautiful, self-consistent vibrations of a single fundamental entity. But there is another path, a rival philosophy that begins its journey from the opposite direction entirely. It argues that string theory, for all its mathematical beauty, makes a critical mistake. It assumes a pre-existing stage, a background of space and time, upon which its strings perform. The second path, known as loop quantum gravity, contends that this is the original sin of modern physics. It takes Einstein's greatest lesson to its absolute radical conclusion. Einstein taught us that gravity is not a force that propagates times through time-space. Gravity times is times the curvature of space-time. The stage and the actor are one and the same. So if we want to create a quantum theory of gravity, we cannot start with quantum things like strings moving through a classical space. We must from the very beginning quantize space and time itself. We must build the stage itself out of quantum mechanical principles. Loop quantum gravity is the audacious attempt to do just that. It is not a theory of matter. It is a theory of the arena of reality, a theory of the fabric of the cosmos. It asks you to forget everything you think you know about empty space. There is no smooth, continuous, infinitely divisible void. According to this theory, if you could zoom in on a region of so-called empty space, you would discover that it is not empty at all. You would find a seething dynamic network of interconnected loops of gravitational field lines. These are not loops times in time-space. These loops times are time-space. They are the fundamental atoms of the spatial geometry itself. Each loop carries a quantum of area, a smallest possible surface. You cannot have a surface area smaller than this fundamental unit, just as you cannot have less than one quantum of light. These loops weave together to form what physicists call a spin network, an abstract graph of nodes and edges that defines the geometry of space at the Planck scale. Where the lines are densely packed, space is strongly curved, creating powerful gravity. Where they are sparse, space is flat. The universe we perceive with its familiar notions of distance, area, and volume is just a large-scale classical approximation of this staggeringly complex quantum tapestry. It means space is not a featureless void, it is a physical quantum system. It's a concept that shatters our intuition. Think of a piece of cloth. From a distance it looks like a smooth, two-dimensional surface, but up close you see it is made of discrete, one-dimensional threads woven together. Loop quantum gravity says that space-time is exactly like this. It is a fabric woven from quantum threads. You cannot zoom in forever. Eventually, you would hit the fundamental pixel of reality, a single node in the spin network, an indivisible atom of space from which the world is built. And what about time? If space is granular, built from discrete chunks, then time must be as well. The smooth, continuous flow of time that we experience is an illusion. In loop quantum gravity, time does not flow. it ticks. The universe evolves through a series of discrete steps as the spin network reconfigures itself from one pattern to another. The evolution of the universe is not a movie, it is a cosmic flipbook. Each page, each tick, is a new geometric arrangement of these fundamental loops. The entire history of the universe from the Big Bang onwards can be thought of as a sequence of these networks, a structure physicists call a spin foam. It is a history of geometry itself, a history without any external clock to measure it by. In this view, there is no background, no absolute stage. There are only relationships. The geometry of space is defined only by how the loops are connected to one another, and the passage of time is nothing more than the constant rewriting of those connections. It is a universe built not on things, but on relations between things. This background independence is the theory's crowning achievement and its most radical departure from string theory. It doesn't need to assume a stage. It constructs the stage moment by moment from pure quantum information. And when loop quantum gravity turns its gaze to the origin of the universe, it offers a vision that is perhaps even more startling than that of string theory. As we trace the universe back towards the singularity, the quantum nature of spacetime becomes dominant. The gravitational field becomes so strong that the granularity of space can no longer be ignored. Because space is made of indivisible quantum loops, it cannot be compressed to an infinitesimal point. There is a maximum possible curvature, a point where the fabric of spacetime itself resists further compression. The theory predicts that the singularity, that point of infinite density where general relativity breaks down, simply does not happen. Instead of a beginning loop, quantum gravity suggests a big bounce. The universe we inhabit may have emerged from the collapse of a previous older universe. As that universe contracted, it reached a point of maximum density, a Planck scale crucible where its geometry was violently reconfigured, and then it bounced back outwards, beginning the expansion that we are still living through today. Our universe might not be the first, but merely the latest in an eternal cycle of cosmic deaths and rebirths, a phoenix perpetually rising from the ashes of its own quantum geometry. It replaces the mystery of the beginning with the grandeur of an infinite cyclical cosmos. So here we stand at a fork in the road to ultimate reality. The two paths before us could not be more different. String theory is a theory of everything in the truest sense. It starts with the ambition to unify all particles and forces into the vibrations of a single entity, and gravity comes along for the ride. It requires a radically new vision of space, one filled with tiny hidden dimensions whose shape dictates the laws of physics. It is a theory of breathtaking scope and mathematical elegance, but it is background dependent, relying on a pre-existing spacetime for its strings to vibrate within. Loop quantum gravity, by contrast, is more modest in its initial scope, but perhaps more profound in its foundations. It focuses solely on quantizing gravity, on rebuilding spacetime itself from first principles. It makes no direct claims about the other forces of nature, but it offers a background-independent framework where the cosmos is a self-contained network of relationships. It doesn't require extra dimensions, but it demands we abandon our most cherished belief that space and time are smooth and continuous. One theory describes the actors on the stage, the other describes how the stage itself is built. They approach the same problem from opposite ends with completely different tools and philosophies. One paints a picture of a symphonic universe, the other a woven one. Both are magnificent intellectual achievements. And both for now remain beautiful mathematical dreams. They operate at energy scales so extreme and distance scales so small that they are far beyond the reach of any experiment we can currently conceive. They exist only on our blackboards in the minds of the physicists struggling to complete them. They are tantalizing visions of how the universe might work at its deepest level, but without evidence they remain just that, visions. The great crisis of the Planck Epoch has given birth to these incredible new ideas, but the path from mathematical possibility to physical reality remains shrouded in shadow. How do we test a symphony played in 10 dimensions? How do we see the individual threads in the fabric of spacetime? The quest for quantum gravity has led us to the limits of theory, and now we must confront the even greater challenge, limits of observation itself. So we stand at the precipice where our two great pillars of understanding have crumbled into paradox. Here at the very edge of existence, time loses its arrow and space dissolves into a quantum fog. It is a place our mathematics cannot enter, a moment our imagination can barely grasp. And for a long time, this was where the story ended, at a wall of infinite ignorance. But human curiosity is not so easily defeated. Where our established laws of physics break down new ideas, audacious and profound rush in to fill the void. These are not mere guesses, but magnificent theoretical structures built by some of the most brilliant minds on the planet. They are our first tentative blueprints for a new kind of physics, a theory of everything that might guide us through the darkness of that first instant. Two rival frameworks lead this charge into the unknown, each offering a radically different vision of creation. On one side, we have string theory, an idea of sublime mathematical elegance. It proposes that if you could zoom in past the quark, past the electron, you would find that the fundamental constituents of reality are not points at all. Instead, you would discover something utterly new, tiny, vibrating, one-dimensional filaments of pure energy, strings. Everything you see, everything you are, the light from a distant star, the chair you're sitting in, the very fabric of your being is just a different note played on these cosmic guitar strings. A different vibration, a different particle, a different force. This simple, powerful idea has a staggering consequence for the problem of the singularity. A point particle with 0 dimensions can be crushed down to an infinitely dense, infinitely hot state. That is the mathematical catastrophe that gives rise to the singularity. But a string is different. It has a length, albeit a fantastically small one, the Planck length itself. It is extended in 1 dimension, and because of this, it can never be squeezed into an absolute nothingness. As you try to compress it, its inherent tension resists vibrating more and more wildly. It effectively smears out the singularity, replacing the infinitely sharp point of the Big Bang with a fuzzy but finite region of vibrating energy. The cataclysmic paradox of the infinite is tamed. The equations no longer scream into absurdity. But to achieve this elegant solution, string theory demands a heavy price. It requires that we abandon our comfortable, familiar notion of reality. The mathematics that makes the theory work, the equations that describe these vibrating filaments, are not consistent in our universe of 3 spatial dimensions and 1 of time. They are only stable, only coherent in a universe with 10 dimensions of space. For a moment, this seems like a fatal flaw, a flight of mathematical fantasy. Where are these other 6 dimensions? We move forwards and backwards, left and right, up and down. There is nowhere else to go. Or is there string theorists propose these extra dimensions? Are they all around us, but they are curled up, compactified into shapes too small for us to ever perceive directly? Imagine a garden hose stretched out across a vast distance. From afar, it looks like a simple one-dimensional line, but for an ant walking upon its surface, there is a second dimension, the circular path around the hose's circumference. Our universe, the theory suggests, might be just like that. We experience the 3 large extended dimensions, but at every single point in space, there exists a tiny, intricate 6-dimensional shape, a Calabi-Yau manifold, a hidden geometric space where the other dimensions are wound up tight. This idea transforms our very conception of the cosmos. Our entire universe, everything we have ever known or will ever know, might be nothing more than a 3-dimensional membrane or brain floating within a much larger 10-dimensional hyperspace called the bulk. We are trapped on this brain like shadows on a wall, while other dimensions and perhaps other brains drift tantalizingly close just beyond our senses. And it is here that we find string theory's most mind-altering prediction about the Planck Epoch. What if our Big Bang wasn't a singular, unique event? What if it was just one event among countless others in this higher dimensional reality? In this cosmic arena, other brains, other entire universes could be moving through the bulk. Over unimaginable timescales, 2 of these brains might drift towards each other. They would accelerate, pulled together by the gravity that leaks between dimensions, until with a cataclysm of unimaginable power they collide. The kinetic energy of that collision would be converted into a firestorm of matter and radiation, igniting a new Big Bang on the surface of both brains. Our universe in this breathtaking vision was not born from a singularity. It was born from a collision. The Planck Epoch was not a moment of infinite density, but the spectacular violent instant when our reality was struck by another. This opens the door to the multiverse, a cosmic foam of countless universes, each existing on its own brane, each with potentially different physical laws determined by the unique way its strings are vibrating. Some might be sterile and dead, others might be teeming with forms of life we cannot even imagine. Our cosmic origin story is rewritten from a lonely miracle to a common, perhaps infinite occurrence in a landscape far grander than we ever dared to conceive. It is a beautiful, compelling narrative, but it is not the only one. Another tribe of theoretical physicists has been exploring a completely different path into the quantum realm. They are the architects of loop quantum gravity. While string theory starts with the particles and forces and tries to incorporate gravity, loop quantum gravity, or LQG, begins with Einstein's greatest idea that gravity is geometry. It takes spacetime itself and subjects it to the strange, pixelated rules of quantum mechanics. In this view, the smooth, continuous fabric of spacetime that Einstein envisioned is just an illusion, an approximation we see at large scales. If you could zoom into the Planck scale, you would see that space is not smooth at all. It is granular. It is woven from an intricate network of finite, indivisible loops. Spacetime itself is quantized. There are fundamental, irreducible atoms of space and time. You cannot have a distance smaller than the Planck length, or a duration shorter than the Planck time. The cosmic fabric has a minimum possible thread count. This seemingly simple principle leads to one of the most profound ideas in all of science. If spacetime is made of indivisible chunks, then it cannot be compressed to a point of zero volume. It has a fundamental, unbreakable limit. As the universe contracts under gravity, the quantum loops of spacetime get pushed closer and closer together. The density increases, the temperature soars, but it can never reach infinity. It reaches a maximum, a point of Planck density, where the granular nature of spacetime itself pushes back. The gravitational force, which is attractive at all other scales, suddenly becomes ferociously repulsive, and at that moment the universe does not end in a singularity. It bounces. This is the Big Bounce. Our Big Bang was not a beginning from nothing, but a moment of cosmic rebirth. It was the triumphant rebound from the collapse of a previous universe. Before our cosmos, there was another, a universe perhaps much like our own that lived its life over billions of years. It had stars that burned and died, galaxies that pirouetted in the dark, and maybe even worlds that harbored their own forms of consciousness. But its expansion eventually slowed, halted, and reversed, leading to a big crunch. Everything, every star, every planet, every black hole was pulled back together into an ever-shrinking, ever-hotter cauldron. But just as it reached the brink of oblivion, at the scale where physics was thought to break the quantum structure of space-time held firm, the universe hit its minimum possible size and, like a compressed spring, recoiled with unimaginable force. The ashes of the old cosmos became the fuel for our own. The Planck Epoch in this telling is the breathtaking moment of transition. It is the cosmic phoenix immolating itself only to rise again from the inferno. Our universe is not an orphan born from an inexplicable singularity. It is the child of a predecessor, part of an eternal cycle of cosmic death and resurrection, a universe that breathes in and out over timescales that defy human comprehension. We are living in the aftermath of the last great exhale, two stunningly beautiful yet mutually exclusive visions of our ultimate origin, a universe born from the clash of higher dimensional membranes, or a universe rebounding from the ashes of its parent. String theory and loop quantum gravity offer us pathways through the forbidden zone of the Planck Epoch. They are triumphs of human intellect and imagination, pushing the boundaries of what we thought was knowable. But right now they remain magnificent stories, elaborate mathematical poems. Science is not poetry. Science demands evidence. And so the greatest challenge of 21st century cosmology is born. How do we test these untestable ideas? How do we find a fossil, a fingerprint, an echo from a time before time, a message from a universe that may have existed before our own? The quest seems impossible. The Planck Epoch was an inferno of such intensity that it should have wiped clean any trace of what came before. It was the ultimate cosmic reset button, and yet there may be whispers. Faint, ghostly messengers from that first instant might still be traveling across the cosmos, carrying secrets of the universe's birth. Our challenge is to build instruments sensitive enough to hear them. The first place we look for these clues is in the oldest light in the universe, the cosmic microwave background. This faint afterglow of the Big Bang, bathing all of space in a cool microwave hum, is a snapshot of the universe when it was just 380000 years old. It is a celestial baby picture, and like any picture, it contains information about its subject's birth. Cosmologists have been mapping this light with ever-increasing precision, and they've found it to be almost perfectly uniform. There are tiny random fluctuations in its temperature seeds of the future galaxies. But what if some of these fluctuations are not random? What if there are subtle patterns hidden in the statistical noise that betray a pre-Big Bang history? The big bounce of loop quantum gravity, for example, predicts that the violent rebound would have sent specific shockwaves rippling through the primordial plasma. These could have left a faint, large-scale suppression of power in the microwave background, a subtle scar on the face of the infant universe hinting at the trauma of its predecessor's collapse. Theorists are calculating the exact signature such an event would leave. Meanwhile, string theory's brain-world collision offers its own set of testable predictions. The impact might not have been perfectly uniform. Some regions of the colliding brains might have hit slightly before others, creating specific non-random patterns like concentric circles or cold spots in the cosmic afterglow. The search is on. Every new satellite, every more precise map of the CMB is a new archaeological dig into the dawn of time. We are sifting through the noise of the cosmos for the faint ordered signal that says something came before. It is a search for a ghost in the machine of creation. But there is another messenger, one even more pristine, more fundamental than light itself: gravitational waves. These are ripples in the very fabric of spacetime predicted by Einstein a century ago. Unlike light, which gets scattered and absorbed by the dense early universe, gravitational waves travel almost completely unimpeded. They are the universe's ultimate eyewitnesses. The Planck Epoch itself, whether a bounce or a brain collision, would have been the most violent event in cosmic history, shaking spacetime with a ferocity that staggers the imagination. It would have produced a storm of primordial gravitational waves, a cosmic birth cry that has been stretching and weakening as the universe expands, but is still echoing through space today. Detecting this gravitational wave background is the holy grail of modern cosmology. Our current detectors, like LIGO and Virgo, are designed to hear the loud chirps of colliding black holes and neutron stars. But the signal from the Planck Epoch is different. It is not a chirp, but a constant faint hum, a stochastic background hiss buried beneath the noise of a billion other astrophysical events. To hear it, we will need to build new kinds of observatories. Instruments in space, like the Laser Interferometer Space Antenna, or LISA, which will create a detector millions of kilometers on a side, using 3 spacecraft flying in a perfect triangular formation. LISA will listen for the slow, gentle swells of these ancient gravitational waves, a frequency far too low for any ground-based detector to ever pick up. It will be the ultimate cosmic ear, straining to hear the vibrations from the moment of creation itself. Each theory makes a different prediction for the exact sound this background would make. The spectrum of the waves, their loudness at different frequencies, would be a direct signature of the physics that govern the Planck Epoch. A bounce might sound different from a collision. A universe born from quantum foam might have a different acoustic signature still. For the first time in history, we are on the verge of turning these metaphysical speculations into a genuine observational science. We have moved beyond the realm of pure mathematics and into the domain of prediction and verification. We are building the machines to go looking for the answers. The quest is monumental, the technical challenge is immense. The signals we are hunting are unimaginably faint whispers from the edge of reality, drowned out by the cacophony of a 13.8 billion-year-old cosmos. It is entirely possible we will find nothing, that the secrets of that first moment are forever scrubbed from the cosmic record, lost to the abyss of time. But it is also possible that in the coming decades, in a stream of data from a new telescope, or in a faint persistent hum from a gravitational wave detector, we will find it. the first definitive piece of physical evidence of a time before the Big Bang, the first clue that our universe is not all there is. That discovery would not just revolutionize physics, it would forever alter our place in the cosmos, transforming our understanding of who we are and where we came from. The answer is out there, written in the fossil light of the Big Bang and echoing in the vibrations of spacetime itself. And our generation is the first in human history with the tools and the audacity to go and look for it. And so our long voyage back through the eons finds its final shore. We have journeyed together, rewinding the colossal expansion of space-time, pushing past the familiar glow of the first stars and galaxies. We navigated the opaque fog of the cosmic dawn, watching as the universe cooled enough for light to travel freely, an echo of which we can still detect today as the cosmic microwave background. From that faint uniform hum, we plunged deeper into the inferno, back through the first 3 minutes where the elemental building blocks of matter were forged. We witnessed the fleeting eras when the fundamental forces of nature, which now govern our reality with such unyielding distinction, were once united in a searing, symmetrical harmony. Each step backward was a triumph of human intellect, a testament to our ability to read the history of the cosmos in the language of mathematics and observation. The story was coherent, the physics was our guide, and the path, while challenging, was illuminated by the lamplight of established theory. Then we took the final step. We crossed the last threshold of our understanding, venturing beyond the last trillionth of a second after the beginning, and arrived here at the edge of the Planck Epoch. It is a destination that is also a barrier, a moment in time that is also the end of time as we conceive it. Our journey, which began with the grand observable universe, has concluded in a realm of pure potential, a dimensionless point of infinite energy and temperature, where every law of physics we hold dear shatters into incomprehensibility. We stand at the base of an infinite wall, a point beyond which our science, our mathematics, our very logic ceases to provide a map. General relativity, Einstein's majestic theory of the macrocosm, predicts a singularity, a point of infinite density that is a mathematical confession of defeat. Quantum mechanics, our staggeringly successful theory of the microcosm, offers no sanctuary, its own principles buckling under the impossible strain of energies that defy its framework. The two great pillars of modern physics, which together explain everything from the graceful dance of galaxies to the frantic jitter of subatomic particles, stand in violent contradiction here at the genesis of everything. It is the ultimate paradox. The moment that created all of physics is the one moment that no current physics can describe. To look upon the Planck Epoch is to look into the face of a profound and humbling ignorance. It is to accept that the story of our universe has a first chapter, perhaps a preface, that is written in a language we have not yet learned to decipher. This realization is not a failure. It is in fact the engine of our deepest scientific ambition. It is the grandest mystery we have ever encountered, a challenge delivered to us from the very dawn of existence. The chasm between what we know and what we are desperate to understand has never been wider, nor has it ever been more tantalizing. It forces us to confront the possibility that our entire conception of reality, of space, as a stage of time, as a flowing river of cause preceding effect, might be nothing more than emergent properties of a much deeper, stranger reality that existed in that first unknowable flicker. Here in this crucible of creation, humility and audacity must walk hand in hand. We are humbled by the sheer scale of the unknown, by the recognition that our most powerful theories are but incomplete approximations of a more fundamental truth. For generations we have built a magnificent cathedral of knowledge, but we now find ourselves at its foundation stone, realizing we have no idea how it was laid or what supports it from below. Yet from this humility springs an ambition of breathtaking scope, the quest for a final theory, a theory of everything. It is an ambition that has driven many of the greatest minds in our history, the dream of a single, elegant mathematical framework that could unite the universe of the large with the universe of the small. A theory that could write the laws of nature in one master equation, the ultimate expression of cosmic order. The Planck Epoch is not merely an obstacle in this quest. It is the ultimate destination, the proving ground where any such theory must face its most rigorous trial. Any proposed theory of everything must do more than just elegantly stitch together gravity and quantum mechanics in the well-behaved universe we see today. It must be able to march unflinchingly into the maelstrom of the Planck Epoch and return with a coherent story. It must be able to look at the singularity predicted by Einstein and see not an end to physics but a beginning. It must explain how a universe of 3 spatial dimensions and 1 of time could spring forth from what? A roiling foam of quantum possibilities, a symphony of vibrating 10-dimensional strings, a network of discrete loops of spacetime. The ideas we have explored, from string theory to loop, quantum gravity, are the first reconnaissance missions into this uncharted territory. They are the products of human imagination operating at its absolute zenith, attempts to build a conceptual bridge across the chasm of our ignorance. These are not just esoteric mathematical games. The answers hidden within the Planck Epoch could resolve the most fundamental questions of our existence. Was the Big Bang truly a beginning, or was it merely a transition in an eternal cyclical cosmos, a big bounce from a previous universe that collapsed? Does the concept of before the Big Bang even have a physical meaning, or did time itself begin its flow in that instant? Are the fundamental constants of nature, the speed of light, the charge of an electron, the strength of gravity, merely random, accidental values frozen in place as the universe cooled, or are they inscribed by some deeper, unavoidable logic? Could a true understanding of this epoch reveal the existence of other universes, a vast multiverse of which our own is but one bubble in an endless cosmic foam, each with its own unique laws and properties? The stakes are nothing less than the very nature of reality itself. Solving the riddle of the Planck Epoch would be more than just the next great discovery. It would represent a paradigm shift in human thought as profound as the Copernican revolution or the dawn of quantum theory. It would be akin to finding the source code of the universe. This quest forces us to reconsider the very nature of scientific inquiry. For centuries, our progress has been guided by observation and experiment. We build ever larger telescopes to see farther back in time, and ever more powerful particle accelerators to recreate the energies of the early universe. But the Planck energy is a barrier of a different kind. Recreating the conditions of the Planck Epoch in a laboratory would require an accelerator the size of our galaxy. We cannot see it with any conceivable instrument, as the universe itself was opaque, and the gravitational waves from that instant, if they exist, are so faint as to be almost mythical. So how do we proceed? We are driven into a new domain of science, one guided primarily by mathematical consistency and sheer theoretical beauty. The search for the theory of everything becomes a search for an idea so powerful, so elegant, and so internally consistent that it simply has times to be right. The universe becomes the ultimate arbiter, and the proof of the theory will lie in its ability to not only describe the Planck Epoch, but also to explain all the features of the cosmos that emerged from it, from the mass of the Higgs boson, the accelerating expansion of the universe today. Think of the generations of inquiry this single infinitesimal moment has inspired. Max Planck himself, stumbling upon the quantum, had no idea his constants would one day define the absolute limit of known physics. Einstein spent the latter half of his life in a frustrating, lonely search for a unified field theory, a dream that his own theory of relativity made both necessary and seemingly impossible. Today, thousands of physicists, mathematicians, and cosmologists around the world are engaged in this grand, collaborative, multi-generational effort. They work on blackboards filled with equations that stretch for yards, they run complex simulations on supercomputers, and they debate the nature of reality in conferences and seminars. They are the cartographers of the unknown, attempting to draw a map of a land they have never seen and can never visit. Their tools are not shovels and picks, but the abstract power of human reason and the boundless reach of imagination. This is the frontier. Not a frontier of space, but a frontier of time and understanding. The Planck Epoch serves as a constant humbling reminder that for all we have achieved, for all the cosmic vistas we have unveiled, we are still just beginning our journey of comprehension. It stands as a silent sentinel at the dawn of time, guarding the ultimate secrets of creation. It challenges us, it taunts us, and it inspires us. It assures us that the age of discovery is not over. In fact, the most profound discoveries may still lie ahead. It is the dark continent on the map of knowledge, and every new mathematical insight, every subtle astronomical observation is another small step towards its shores. It guarantees that for generations to come, there will be young minds who look up at the night sky and are not content with just knowing times what times is there, but are consumed by the burning need to understand time's why asterisk. Why is there something rather than nothing? Why does the universe follow these particular laws? What happened in that first ultimate moment? As we draw our exploration to a close, we leave you here at this precipice of understanding. The story of the universe as we can tell it is a magnificent and sprawling epic, yet we must now concede that it begins in the middle. The true beginning remains shrouded in the mystery of the Planck Epoch, a puzzle box locked by the combined limits of our two greatest theories. Finding the key to that box will not be the work of a single person or a single nation, but of all of us, of humanity's unrelenting and shared curiosity. And when that key is finally turned, it will not merely open a door to the past, it will unlock a new future for our understanding of everything. It will revolutionize our conception of space, of time, and of our own place within the grand unfolding tapestry of the cosmos. The ultimate origin story is still waiting to be told, and its revelation will undoubtedly be the greatest intellectual adventure in the history of our species. The quest continues.